Now we can use the fundamental matrix between the three views that we denote as F21, F31, and F32. We have three views over here: first view, second view, and third view. F21 relates the first and second view over here, and F31 relates the first and third images over here, and F32 relates the second and third image over here. So we want to ask the question of, given the two correspondences between the first and second images, which we denote as x and x prime over here, can we make use of the known fundamental matrices F21, F32, and F31 to transfer the correspondence between the first two images denoted as x and x prime into the third view. Hence, this can be rephrased as we want to find this particular point over here, x prime prime, from the known fundamental matrices and the known correspondence in the first two view. The answer is yes, of course, and can be simply found by the intersection of the epipolar lines formed by x and x prime in the first two views. And let's see how it's going to be done. So in the first view over here, we can transfer the point x in the first image via the fundamental matrix denoted by F31 into the third view as the epipolar line. So in the earlier lecture on fundamental matrix, we know that this particular epipolar line over here, which we denote as L13, for example, it's going to be equals to the fundamental matrix of 3, 1 multiplied by x over here. And we can do the similar thing to transfer the point from the second image, which we denote as x prime, onto the epipolar line in the third image via fundamental matrix that relates the second and third view over here. And this is more explicitly written as L23 equals to F32 multiplied by x prime over here. So we know that these two epipolar line, the correspondence in the third view must lie anywhere in both of these epipolar lines. Hence, the intersection over here would give the correspondence x prime prime over here. And this can be written in this particular equation over here, where the first term over here represents the epipolar line of the first image x over here onto the third image, which we denote as L13. And the second term here would be the second image x prime, transferring it to the third image as the epipolar line, which we denote as L23 over here. And the cross product is going to give us x prime prime over here. So unfortunately, this quickly run into a degenerate case. The two epipolar lines that is being transferred from the first image of x into the third image, this particular epipolar line over here, it is collinear with the point x prime from the second image transferred onto the third image. When these two lines becomes collinear, then in this particular case, x prime prime, the third correspondence over here, remains undefined because it could be anywhere on this particular line that joins the two epipolar lines. So we can see that with the use of trifocal tensor, this degeneracy will no longer exist. And we saw earlier on that from the point line point incidence relation that is given by this equation over here, that the transfer of a point from the first view x over here, from the first view to the third view, it's not degenerate. And however, there's also a special case over here where this transfer becomes undefined, but we will see that this can be easily avoided by a simple choice of the line L prime over here. So here is worthwhile mentioning that this particular point line point relation, the transfer of the first point in the first view over here, denoted by x over here, into the third view as x prime prime over here would be via something that is similar to the homography that we have seen earlier on. So this would be a homography transfer between the first view and the second view. And this homography transfer is defined by the back projection of the line. That means that it's this plane over here in the second image and the trifocal tensor and that we have seen earlier on in the lecture. And in this case over here, when L prime that defines the homography is the epipolar line of the second view. That means that this particular line over here, L prime, it sits on the epipolar plane together with the back projected ray from the point X that creates this particular epipolar plane and the epipolar line in the second image, then the relation over here, the transfer relation that we have seen over here, it becomes 0. So this means that this guy over here is always going to be 0, and hence x prime prime cannot be found in this particular case over here. The reason why is because we can see that this L prime over here, which is the epipolar line, exactly defines the relation that we have seen earlier on. So L prime here, it lies on the null space of xi multiplied by ti over here. This relation over here, as what we have seen earlier on, regardless of whatever point of x over here, is always going to be equals to 0 since it's in the null space of this term over here. So easy solution out here would be to simply select the line that passes through x prime as the line that is perpendicular to the epipolar line formed by the transfer of x into the second view. So here, if L prime E over here, which is the epipolar line of x from the first view transferred into the second view via F21, we denote it as L1, L2, L3 transpose over here. The correspondence point in the second view to x. So this means that I have the first image, which is a point x over here, and the corresponding view over here is x denoted by x prime over here. The epipolar line, we denote it as LE prime, which is given by this guy over here, and x prime, we denote it by the homogeneous coordinate as x1, x2, and 1, which it denotes this point, which is the corresponding point to the first point x in the first image over here. Then a best choice of L prime would be the line that is perpendicular to the epipolar line and intersects with the epipolar line at the point of the corresponding point x prime over here, as indicated by this particular equation over here. So what this means is that since we know that the selection of at the epipolar line for this homography over here, it's going to cause a degeneracy. What it means is that we know that L prime can be any line as long as it passes through x prime in the second image over here. So a best choice this L prime over here would be a line that is perpendicular to the degenerate case of the epipolar line, which we denote as LE over here. And that's going to be given by this equation over here. So I'm not going to derive this. I will leave it to you to prove that this is the perpendicular line that is formed by the epipolar line and intersects at the point x prime over here. Hence now the transferred point is given by this equation over here, where the choice of L prime over here is guaranteed that this term won't degenerate. It will never be 0 over here. Now finally we'll look at the computation of the trifocal tensor from the image correspondences. So we have seen that earlier on that the incidence relations can be defined in Threeviews using points and or lines. And so given several of these point or line correspondences between the three images, we can rewrite the incidence relation in the homogeneous linear form given by this AT equals to 0 over here, where T here is the 27 by 1 vector that is made out all the entries in the trifocal tensor. And because we know that each Ti is a 3 by 3 matrix and we have 3 times of this, so altogether we have 27 entries in the trifocal tensor. So expressing it in the linear form like this, At equals to 0, means that we need 26 or more equation to find the least square solutions that is computed by this equation over here, subjected to the constraint that the norm of the trifocal tensor vector has to be equals to 1. So we saw many times in the earlier lectures that this minimization here can be solved using the singular value decomposition method. And here's a table of the uh, linear equation that is from the incidence relationship that we have defined earlier on. So we can see that 3-point correspondences here. It gives us a total of 4 linearly independent equations in this particular form, expressed as a tensor notation. And 2 points and 1 line gives us 2, and so on and so forth. So here, notice that S, T, and W over here, the indices over here, is no longer 1, 2, and 3. It's actually just denoting 1 and 2. For example, in this case here, 1 and 2, you will give us 4 entries over here, which is 0 to equals to 0, and that would be 4 equations. And the reason why this is not equals to 1, 2, and 3 is because of the rank deficiency in the trifocal tensor. So here we note that the first line in the table over here, in the original incidence relation, it has to be of a choice of ST equals to 1, 2, or 3. That's in total, it will give rise to 9 equations over there. But in this particular case, where because we know that the trifocal tensor, it's a rank deficient tensor, where each one of the 3 by 3 matrix in the trifocal tensor is only of rank 2. Hence, there are only 4 linearly independent equations in this coincidence relation over here, and hence we will drop the index of 3 over here and only evaluate for the 4 combinations of S and T, where each one of them takes 1 and 2 respectively. So this is, as I mentioned earlier on, this is due to the rank deficiency, but the proof to this is rather complicated, and we will not cover this in this particular course. So once we have obtained the equation, the linear equation AT equals to 0 in this case over here, where T is 27 by 1 vector, and we saw that the solution can be obtained from taking the SVD of A. But we also saw in the earlier lectures when we compute homography and when we compute fundamental matrix, that is that the A matrix over here, the coefficient matrix over here, it's actually formed by the image correspondences, which might not be distributed evenly in the image. So as a result, the magnitude of the entries in A might differ significantly from each other, and hence it's going to cause the SVD result to be very unstable. So we saw earlier on in the lecture on homography and fundamental matrix that a step of normalization is compulsory to prevent this ill conditioning from happening. So we'll apply the same normalization steps over here, where we'll first do a translation on the image correspondences such that the centroid of all the points is shifted to the origin of the reference frame. And then we will apply a scaling to these transform points such that the average root mean square distance from all points to the centroid, it's equals to square root 2. This ensures that the magnitude in the A matrix over here is even or is within a very narrow range, such that A becomes a better conditioned matrix to be put into the SVD to get the solution. And in case of line correspondence, we will simply do the transform by considering the line's two endpoints. So what this means is that if I have a line here, I will transform all these lines in the image using these endpoints over here. So that means that I have x1, x2, x3, x4, x5, and x6, for example. Then I will compute the similarity transform matrix using the translation and the scaling method that is defined here, and apply it onto every respective endpoints over here. So once I get the transformation, I will apply it onto this, and then I will get a transform point x1 tilde x2 tilde that defines the new line over here. So here's a summary on the normalized linear algorithm for the computation of the trifocal tensor. So since there are 27 unknowns in the vector that we saw earlier on, in this case AT, that we want to minimize. So this means that we need a minimum of 26 equations to solve for these 27 unknowns over here. And for the case of point correspondences across the three images, we saw that each one of these point correspondence gives us four linearly independent equation. So this simply means that we need 7 point. If in the case where there's only a point correspondences across the three images, that will altogether gives us 7 multiplied by 4, which is 28 linear equations over here, and that will give us the enough constraints to solve for these 27 unknowns. In the case where there are three line correspondences across the three different images, we will make use of 13 line correspondences, since we see that each of these line correspondence is going to give us two constraints, two equations over here. So the 13 multiplied by 2 is going to give us 26 equations, 26 linearly independent equations, which is sufficient to solve for the 27 unknowns over here. According to the different mixture of point or line correspondences here in this particular table, we can make use of the number of independent constraints over here to determine the minimum number of line or point correspondences that we need to compute the trifocal tensor. So we will follow the same step as before, that to solve this linear equation, we'll do a transformation. This is the normalization that we seen earlier on. We'll apply the normalization in each one of the respective image, and then we will compute the tensor linearly using this equation over here, using the SVD equation over here. So once we get T, we can denormalize it to get back the trifocal tensor in the original point or line corresponding setting. Now, similar to the fundamental matrix, that after we solve for this equation over here, after we do a argmin over f over here, subjected to the constraint that f has to be equals to 1. So similar to this particular case, the fundamental matrix that is being recovered here by reshaping the vector of f over here into a 3 by 3 matrix over here, we saw earlier on that this is not a valid fundamental matrix in most of the cases, because the rank is not equals to 2 over here because of the noisy measurements in A. So the rank of the F over here, the fundamental matrix over here, is not going to be 2 due to the noise. And we can enforce this to be rank 2 by doing a Frobenius norm minimization, and by forcing the epipole to be intersecting at a common point over here. So in the case where the rank is not equals to 2, we saw earlier on that the epipole will not have a unique definition. And here, in the case of the trifocal tensor, we did the same thing by doing the minimization over T, A, T over here, subjected to the norm of T to be equals to 1. So here, after we solve for T and reshape it into the trifocal tensor over here, we note that this is also not going to follow the rank 2 constraint that we saw earlier on. And what happens here is that if it doesn't follow the rank 2 constraint, then the epipole that we saw that we can extract from the trifocal tensor will also not be uniquely defined, as in the case of the fundamental matrix. So we can enforce the epipolar constraints on the trifocal tensor after we compute the tentative trifocal tensor T1, T2, T3 by minimizing the norm of AT subjected to the constraint that the norm of T has to be 1. So here uh, we can use this as a tentative trifocal tensor over here T1, T2, T3, and recall that earlier on that given a trifocal tensor T1, T2, T3 over here, we can compute the epipolar lines uh, in the third view, which we now denote as V1, V2, V3, that corresponds to three special points denoted by 1, 0, 0, 0, 1, 0, and 0, 0, 1 over here. And that's simply the right null space of the respective Ti 3 by 3 matrix that is obtained from the trifocal tensor that we computed earlier on using normalized linear algorithm. Now, solving this equation over here for the right null space, we will get the three epipolar lines over here. And then the next step we can do here is that we know that these epipolar lines, these three epipolar lines, V1, V2, V3, they have to intersect at a certain point, which is the epipole that we denote as E prime prime over here. And that can be obtained by solving for the left null space of this particular matrix that is obtained from the concatenation of the three epipolar lines over here that we have seen earlier on. But in general, as we have mentioned earlier on, that because the image correspondences that is obtained from the image observation is often corrupted with noise. This means that the A matrix that is used to compute the trifocal tensor is also corrupted with noise. Hence, the trifocal tensor will not fulfill the rank 2 constraint, and the epipole that is being constructed here might not fulfill this condition that it will intersect at a certain point. So the correct way to do this is that in the presence of noise, we should minimize the norm of this T uh, multiplied by V over here to solve for the null space of this guy over here. Um, and because in a case of the inaccurate trifocal tensor that is obtained from the noisy A, Ti multiplied by Vi will never be equals to 0. Hence, the obvious way to do the minimization would be to minimize the norm of this guy over here, such that it becomes as close to 0 as possible by doing an arcmean over Vi, which is our epipolar line that we wish to solve for. We'll do the same thing for when we solve for the null space of the epipole, because we know that this guy here is solved from the A matrix that's corrupted with noise. Hence, this relation will not be equals to 0. So the solution that we've seen earlier on is to minimize the norm of this guy over here instead. We'll do the same thing because we know that V here is computed from a trifocal tensor that is computed from A that is corrupted with noise. Hence, the relation over here will also never be equals to 0. So the obvious choice to do here would be to simply minimize the norm of this for E over here, and this can be solved using the SVD technique that we have seen earlier on. So now, once the epipoles are solved in the second view and the third view, which we denote as E prime as well as E prime prime over here, we know that the two columns, the last column of P prime and P prime prime would be known because we saw that the P prime over here is equals to A4 over here, and this A4 over here is simply equals to E prime, and P prime prime over here is equals to B and B4 over here, where B4 here is simply equals to E prime prime over here. So we since we have solved the E prime and E prime prime earlier on using the from the trifocal tensor, we can rewrite the trifocal tensor relation linearly in terms of the entries in the two camera projection matrices over here. And this can be rewritten in terms of this trifocal tensor relation that we have derived earlier on, which is a function of all the entries in the two camera matrices. So since this is a linear equation in terms of all the respective entries in P prime and P prime prime, what we can do here is that we can factorize this into E multiplied by a vector of A, where the vector of A here, it consists of the remaining entries A and B in P prime and P prime prime. So because in this case here we have already solved for E prime and E prime prime, which corresponds to the last column of P prime and P prime prime. So the remaining unknowns here would be the entries in capital A and capital B, the first 3 by 3 matrix of the respective camera projection matrix. And we know that this relation over here, it's equivalent. It represents the respective entry in the trifocal tensor. So in a linear relation, so we can rewrite this relation in terms of this, where E consists of all the known entries, and A over here is a vector that contains the remaining unknown entries in the two respective camera projection matrices. Now, having formalized this, where we now rewrite T here in terms of this linear multiplication over here of a matrix and a vector over here, where E contains all the known values from the epipoles, and A here contains all the remaining unknown entries in the two camera projection matrix over here. We will simply minimize the algebraic error that is given by this guy over here, subjected to the fact that EA has to be a norm of 1, because EA here represents T here, which is equivalent to minimizing AT subjected to the norm of T to be equals to 1. And once we have solved for this equation over here, since we know that E over here, it comes from the known epipoles, which is the condition that we have enforced earlier on. Hence, solving for the remaining entries in T according to the unknown entries in the two camera matrices denoted by the vector A over here, means that the entries of the trifocal tensor would have inherently enforced the epipoles that we have solved for earlier. And finally, the trifocal tensor that is being solved from the algebraic error that we have seen earlier on serves as an initialization for the optimization using geometric distance that we have seen in the case of the homography as well as the case of the fundamental matrix. So here we'll make use of the linear algorithm that we've seen earlier on to provide an initial estimate for the trifocal tensor. Then we can pretty much retrieve the camera matrices. So P would be the canonical camera matrix, P prime would be what we have seen earlier on, and P prime prime would be also what we have seen earlier on from the trifocal tensor T. Then we will make use of the correspondences in the Threeview and the respective camera matrices to determine the 3D point via the linear triangulation method that we have seen earlier on in the chapter of fundamental matrix. What this means is that once we have these three views, all the camera matrices P, P prime, and P prime prime, we can make use of this to the X prime and X prime prime over here to do a linear triangulation to get the point, the 3D point X over here. But since there is an uncertainty or there's an error based on the uncertainty, the noise of the observed image correspondence over, we are sure that P prime and P prime prime would never be the exact case. So what happens here is that X from the linear triangulation algorithm would be the optimal point for the intersection of these three back projected light ray according to P prime, P prime prime, and P itself. But what it means here is that if I were to reproject this X over here back onto the images, let's say this is my observed point X, the reprojected point is never going to be the same on the same location as X. My observed point, I'm going to denote this as X hat over here, is never going to be the same location over here. So there is a geometric error over here, which can be computed by the Euclidean distance between the reprojected point x hat and the observed point x over here. So this distance over here would be denoted by these three terms over here, and these terms over here represents the respective reprojection of the triangulated point into every single image. So what we want to do here is that we want to minimize these reprojection errors over here over the 3m by 24 variable for the n3D points, as well as the 24 elements in p prime and p prime prime, because p here is simply I and 0, and there's no need to optimize over this guy over here. But we'll look at this equation over here in more detail in the next lecture, because this is equivalent to a Threeview bundle adjustment that we will look at in more detail in the next lecture. So as a summary, in today's lecture, we have looked at how to derive the trifocal tensor constraint for Threeviews using point and or line correspondences. And then we have described the homography relations using that is obtained from the trifocal tensor. We have also looked at how to extract the epipoles and epipolar lines in the second and third view from the trifocal tensor. Furthermore, we have also looked at how to decompose the trifocal tensor into the camera matrices as well as the fundamental matrices of the Threeviews. Finally, we look at how to compute the trifocal tensor in both the algebraic way as well as the geometric way from point and line correspondences in the Threeviews. Thank you.